Okay, so in this section, guys, we're talking about dividing radical expressions. That's the title of the section. That's the goal. In this section, the big property tells us how to divide radicals. And so one way to write it would be this. If you want to take the nth root of A and divide it by the nth root of B, well, just like with multiplication, it turns out you can combine that division of two separate radicals as long as the indices are the same. You can combine that into a single radical, just like with multiplication. And so this is going to be one big nth root, and then divide the radical as A divided by B underneath that new radical. And the equal sign's a two-way street, right? So it might be that you use this big property in this direction. The nth root of A divided by the nth root of B is equal to the nth root of A divided by B. Or maybe you'll split it up. Maybe you'll go the other direction. The nth root of A divided by B is equal to the nth root of A divided by the nth root of B. And it just depends on what example you're working as to which way you'll go. Okay? All right, let's give it a shot.
Example, simplify. Now, it really is simplifying, but it's also a division problem, isn't it? Underneath that radical, it's a division problem, so that's why we're including this problem in this section. So in part A, it says simplify. We have the square root of 121 divided by x squared. So what could you do here? Which way would you want to use the big property? Would you want to break up the root? It's already one root, so you can't combine it, right? Let's break it up and then just take square roots. So I'll bet you could have done this one without me talking about it today. It's the square root of 121 over the square root of x squared. So if we assume variables are non-negative, what are we going to get for a final answer here? 11 over x. And I'll just put parenthetically, or 11 over what if you don't make the assumption that variables are non-negative. Yeah. Or 11 over the absolute value of x if variables can be negative. In this case, if I could just put if x can be negative. Okay. Is x going to equal 0 in this case? No, and that's just the natural assumption. Oh, yeah, we can't divide by 0. You guys could have done that one without me. Let's go on to the next one. So in part B, we have the fourth root of x to the ninth, y to the 12th, divided by z to the 6th. Now, we just did a homework problem where the radicand simplified, right? Does the radicand simplify here? No, but you should be on the lookout for that. So I don't have any like bases going on under there. So I think the best thing to do, if I want to simplify this as much as possible, I can go ahead and split up the root over division. So using the big property, I get the fourth root of x to the ninth times y to the 12th over the fourth root of z to the 6th. Okay. Well, I don't have perfect fourth roots, or perfect fourth powers, that is, underneath the radicals, but I do have factors, some factors in both radicands that are perfect fourth powers, don't I? So I can basically simplify the numerator, simplify the denominator in the way that we looked at yesterday. So let's just take the numerator separately from the denominator, do one thing at a time. So looking at the numerator, can you pull out the next power of x down from x to the ninth? That's a perfect, we're looking for perfect fourth powers because the index is 4. So can you do that? So x to the 8th. All right, so it's the fourth root, x to the 8th. What's left? No, what's left from the x to the ninth? Just a factor of x. So I'm going to write that over here, kind of off to the side. The non-perfect square factors I like to separate. What about y to the 12th?
It's already a perfect fourth power, isn't it? So I'll leave that as is. And then if I want to go ahead and do it all at once, let me scoot this over. What can I pull out then? What's the square root, or I'm sorry, the fourth root of x to the 8th? What's the fourth root of x to the 8th?
X squared y cubed.
X squared. And then, right, the fourth root of y to the 12th is y cubed. Pull them out. So the numerator is as simplified as it's going to get. I'm going to clean it up in the next step, but does that make sense? Okay, now let's do the denominator. Z to the 6th. How can you break up z to the 6th? We're looking for a perfect what power of z? Because the index is 4, we're looking for a perfect fourth power. What's the next power of z down from z to the 6th? That's a perfect fourth power? Well, z to the 4th, right? So z to the 4th, what's left? Z squared. Okay. What's the fourth root of z to the 4th? Z. So we pull out a z. Okay, all that's left to do is clean it up. So make it x squared y cubed times the fourth root of just x. Then z, I suppose there is something you could do with this. Do you guys see that in the denominator we have a factor of z to the 4th? I'm sorry, z squared. It's actually the fourth root of z squared, isn't it? So there is something I taught you to do on this. Yeah, you can reduce it to the square root of z. Do you guys see why? If you rewrite this using a rational exponent, what is the fourth root of z squared? It's z to the what power? 2 fourths, which is the same as z to the 1/2. So I suppose if you wanted to, you could reduce that fourth root of z squared to z to the 1/2, which is the square root of z. Although I'd be happy if you just had z times the fourth root of z squared. That would be cool with me, unless I explicitly said otherwise.